Welcome to today's paper reading. Today's paper is titled, Reasoning with Reinforced Fine-Tuning. This paper was published on the AR14 preprint by Trung, Quoc, Luong and colleagues from ByteDance Research. The abstract discusses the enhancement of large language models, LLMs, through supervised fine-tuning, SFT, using chain-of-thought, COT, annotations. However, this approach has limited generalization due to reliance on a single reasoning path per question. To address this, the authors propose reinforced fine-tuning, ReFT, which involves a warm-up phase with SFT followed by online reinforcement learning using the PPO algorithm. This method samples multiple reasoning paths and derives rewards from ground truth answers. Experiments on GSM-8K, MathQA, and SVAMP datasets demonstrate that ReFT significantly outperforms SFT, with potential further improvements through inference time strategies like majority voting and re-ranking. Notably, ReFT achieves this without additional training questions, indicating superior generalization. The current leading methods for solving math problems use supervised fine-tuning, SFT, with chain-of-thought, COT, annotations. However, these methods often result in models with relatively weak generalization abilities. To address this, the authors propose reinforced fine-tuning, ReFT. ReFT begins with a warm-up stage involving SFT, followed by reinforcement learning training to enhance the model's generalization. Additionally, ReFT benefits from techniques like majority voting and reward model re-ranking at inference time, which further improves its performance. Figure 1 illustrates an example of a question, its chain of thought, COT, annotation, and the answer from the GSM-8K dataset. The SFT process involves iterating over the training data for several epochs. The ReFT process begins with a warm-up phase using SFT and then employs reinforcement learning on the same data. This example shows how Wang's earnings are calculated by converting the time worked from minutes to hours and then multiplying by her hourly rate. In the field of math problem solving, recent research has focused on the design of chain-of-thought, COT, prompts and data engineering. Studies have aimed to make COT comprehensive and fine-grained, presenting step-by-step reasoning solutions. Notably, Gao et al., 2023, proposed using Python programs as COT prompts, demonstrating more accurate reasoning steps. In reinforcement learning, our work relates to applying proximal policy optimization, PPO, for aligning human preferences. Several training algorithms have been proposed to improve alignment efficiency. Our approach, reinforced fine-tuning, ReFT, utilizes reinforcement learning to solve math problems, showing enhanced generalization capabilities. We conducted experiments on foundational models like CodeLlama and Galactica across standard datasets, demonstrating improved performance over conventional supervised fine-tuning. Figure 2 illustrates the contrast between supervised fine-tuning, SFT, and reinforced fine-tuning, ReFT, in the context of chain-of-thought, COT, alternatives. It highlights how ReFT, through the use of reinforcement learning, can sample multiple correct reasoning paths or COT annotations, thereby enhancing its generalization capabilities in solving mathematical problems compared to SFT. This figure underscores the significant improvement in performance and generalization ability that ReFT demonstrates over SFT, especially when trained on the same dataset without requiring additional or augmented training questions. In this work, the authors focus on two types of chain-of-thought, COT methods, natural language COT, ENCOT, and program-based COT, PCOT. ENCOT involves using natural language for problem solving, while PCOT uses Python programs. The reinforced fine-tuning, ReFT, process is divided into two stages, the warm-up stage and the reinforcement learning stage. During the warm-up stage, the model is fine-tuned on datasets containing question, COT, tuples to develop basic problem-solving skills. In the reinforcement learning stage, the model improves by learning from question-answer tuples. The reward function is designed to give a reward of 1 for correct answers and 0.1 for partial correct numeric answers, with the total reward also incorporating the Kuhlbach-Leibler divergence. In this section, we discuss the experiments conducted on 3 math problem datasets, GSM-8K, SVAMP, and MathQA. These datasets include both numeric value answers and multiple choice formats. Table 1 provides an overview of the dataset statistics. We employed few-shot prompting using GPT 3.5 Turbo to obtain NCOT and PCOT annotations, following specific methodologies. Additionally, an experiment was performed on a numeric version of MathQA to explore potential reward hacking phenomena. We compared our ReFT method with several baselines, including SFT, offline self-training, offline ST, and online self-training, online ST. The performance comparison is detailed in Table 2, showing that ReFT consistently outperforms these baselines. Table 1 provides an overview of the training and testing dataset statistics. For GSM-8K, there are 7,465 training examples with NCOT annotations, 7,356 with PCOT annotations, and 1,319 test examples. SVAMP has 3,076 training examples with NCOT annotations, 3,043 with PCOT annotations, and 1,000 test examples. MathCamp includes 14,862 training examples with NCOT annotations, 15,250 with PCOT annotations, and 1,605 test examples. These statistics highlight the distribution of annotated data used for training and evaluating models in the experiments. Table 2 presents the value accuracy of ReFT and various baselines fine-tuned with 2 foundation models across multiple datasets. The data reveals that ReFT consistently outperforms the SFT baseline, achieving significant improvements in accuracy. Specifically, ReFT shows a 10-point increase in accuracy on the GSM-8K NCOT dataset when using the Code Llama model. On average, ReFT achieves a 7.4-point improvement across all datasets with the Code Llama model. These results highlight the robust generalization capabilities of ReFT and its potential for further exploration in training methodologies. Table 3 illustrates the value accuracy of ReFT compared to several baseline methods using 2 foundation models, Galactica and Code Llama, on the MathQA numeric benchmark. The data includes results from reinforcement learning studies. ReFT demonstrates superior performance over standard supervised fine-tuning, SFT, and self-training approaches, indicating the importance of exploration in ReFT's methodology. Despite some improvements from online self-training with Galactica, ReFT remains significantly more accurate on average. The table also highlights the issue of reward hacking in the training of MathQA MCQ, where incorrect instances can mislead the model, emphasizing the need for more refined reward mechanisms. Figure 3 illustrates an example of reward hacking in the prediction of MathQA MCQ. The sampled chain of thought, COT, produces an incorrect answer 172, which is not half of the product of 18 and 22. Despite this, the final reasoning step predicts option C as the answer, as the model always predicts one of the options from A, B, C, D, E. This misleading COT receives a positive reward 1, leading the model to treat it as a correct COT. This reward hacking phenomenon severely affects model training. Table 4 presents the solving accuracy of majority voting and reward model re-ranking for SFT and ReFT on the GSM-8K dataset. The table highlights that ReFT consistently outperforms SFT in both voting and re-ranking scenarios. Specifically, ReFT plus voting significantly improves accuracy by 8.6 points on average compared to SFT plus voting. Additionally, ReFT with re-ranking shows more than a 3-point improvement over SFT with re-ranking. The table also includes comparisons with existing open-source approaches, demonstrating that the best PCOT variant of ReFT achieves the highest accuracy of 81.2 on GSM-8K, surpassing even GPT 3.5 Turbo. Table 5 presents the results of experiments conducted on the PCOT data using 3 small language models, Galactica 125M, CodeParrot Small, and CodeGen 350M. The table shows a comparison between the performance of SFT, Supervised Fine-Tuning, and ReFT, Reinforcement Fine-Tuning. Notably, ReFT consistently outperforms SFT across these 3 datasets, highlighting the robustness of ReFT in the exploration of reasonable programs. This performance improvement underscores the effectiveness of ReFT in scenarios involving small language models. Table 6 presents an ablation study on the GSM-8K PCOT dataset, focusing on the impact of removing the partial reward, setting the KL coefficient beta to 0, and using a separate value model. The study reveals that without the partial reward, ReFT's accuracy drops to 74.4 but remains superior to SFT. Setting beta to 0 results in a policy distribution collapse, highlighting the importance of constraints. The use of a separate value model accelerates early convergence but increases computational overhead. Figure 4 illustrates the training metrics of ReFT on the GSM-8K Quoc dataset. It shows the mean training reward, evaluation accuracy, and KL divergence against the training epoch. Notably, the mean training reward stabilizes around 80 to 90% by the 40th epoch, indicating effective policy exploration. The evaluation accuracy continues to rise, suggesting improved performance over time. The KL divergence, initially high, settles within a reasonable range of 0 to 10, reflecting stable policy behavior. Table 7 presents the qualitative scores of 3 models trained on the GSM-8K Quoc dataset. The scores are based on logic, naming, compactness, and an overall score. ReFT shows a slight edge over SFT and significantly outperforms the warm-up variant, particularly in the compactness criterion. This indicates ReFT's robustness in generating accurate and semantically coherent reasoning paths, despite the close overall scores. In this study, the authors introduce a new method called reinforced fine-tuning, ReFT, designed to fine-tune models for solving math problems. Unlike supervised fine-tuning, SFT, ReFT focuses on optimizing non-differentiable objectives by exploring multiple chain of thought, COT, annotations to find the correct answer, rather than relying on a single annotation. Through extensive experiments on 3 datasets using 2 foundation models, ReFT has been shown to outperform SFT in terms of both performance and generalization ability. Additionally, ReFT is compatible with techniques such as majority voting and reward model re-ranking. The authors also note that ReFT has demonstrated superior performance compared to several publicly available open-source models, highlighting its effectiveness and practical value. Looking ahead, the authors plan to apply the Proximal Policy Optimization (PPO) algorithm to fine-tune large language models (LLMs) for math problem solving and explore offline reinforcement learning techniques to further enhance training efficiency and performance. They also aim to develop a warm-up free method to reduce the gap with re-ranking methods and explore the implementation of process-based rewards and reinforcement learning training. Figure 5 illustrates the accuracy comparison between the supervised fine-tuning (SFT) and reinforced fine-tuning (ReFT) models with varying warm-up epochs. Notably, all ReFT variants demonstrate superior performance to SFT, with a significant margin. Initially, after the warm-up phase, the performance of all ReFT policies declines until around the 8th training epoch, attributed to the random initialization of the linear layer in the shared value model. From the 30th epoch onwards, SFT converges while ReFT variants continue to improve. Interestingly, no specific ReFT variant shows a clear advantage over the others. Thank you for watching.